All right, so I think the most important thing is about the upcoming final test, okay, before the exam. So you already got an E-class announcement from me yesterday, or maybe today, I forgot. But anyway, it's about a guide. So if you go to the lecture site, you will see that there is a guide here about written test number 2. So take a look at that. I think the format will be very similar to your written test number 1, except that this time, I will make the event B summary file to you as well as before, but I think you have to pay attention to the inference rules that we actually already covered. So I think without any surprise, I think that you will need the first 2 sets over here. So I already made a PDF over here, so inference rule number 1 and number 2. So these are the ones covered so far. Okay, we're going to do a little bit more application today and also Thursday, but that's something you want to get familiar with. But I'll make these 2 files available to you as well. Again, if you want to print them out, no problem. That's okay. Just keep them clean if that can help you. All right. And then, guys, it's very important, just in case you haven't, it's not really disastrous just yet, but you want to make sure you catch up with the lecture from last Thursday. Okay, so it's already there. So it's really about right here, right? So about last Thursday. Okay, please catch up because that one there is going to be kind of covered. For sure, they will be covered next Wednesday in your written test number 2. All right. So today, I would just like to do a very quick recap about what you should really pick up from the last Thursday's lecture, and then just revisit about the idea about deadlock freedom, and then I would like to continue from there and doing more analysis today. And then we're going to move on to the first refinements for the bridge controller. That's what we want to do. Okay. Let me see if I missed anything from here. Okay. So let's say, okay, written test 2 next Wednesday, the guide, and the practice question, right, is already there. Take a look. And there might be a past recording about going over the question one by one. I'll dig it out and I'll make it available to you earlier, so you can also take a look. And then your Lab 3 solution, I know Lab 3 is only due next Tuesday, which is 1 day before your written test 2. So what I will do is, I'll just let you guys maybe try it out for a couple of days. I'll try to make Lab 3 solution available before Thursday's class, so you can also take a look. That's not a problem. Just make sure you still submit your best attempt before the submission deadline, right? Policy the same. You submit your best attempt before the deadline, you get 100%, right? No question asked for the lab. Any questions about the course? Yes?
Yeah, I always have your question regarding your lab evaluation. So does that mean that once we submit it, you know we submitted, you don't look at what's inside, then you give 100%?
So it's more like a matter of trust, right? I kind of trust you, you will submit your best attempt. I really have total trust. So of course, if you, how exactly you define best attempt is kind of up to you. I trust that you kind of try your best before the submission deadline. And then I also give you my solution. You can take a look. So I'll just kind of test you on that, maybe on the subsequent evaluation, really.
Okay, thank you. And second question is regarding the content of the written exam. Are you going to cover all the way to like next Tuesday's lecture?
Not next Tuesday. So if you, okay, again, yeah, I think it's good to clarify. So guys, if you look at the guide for written test number 2, right? So it is going to cover basically from slide number 2 of the bridge controller, right, the beginning basically, all the way until and including what I'm going to cover on Thursday. All right, so we'll confirm exactly the slide number on Thursday. So as soon as I finish the lecture on Thursday in person, I'll confirm with you, okay, which slide. Okay, but I more or less know where I'm going to cover until. But let's see. But of course, if you guys have to slow me down, ask questions, no problem. I can cover less. That's not a problem. Okay. So is that all your question, or you got more?
Exactly.
Okay. Yeah, no worries. But you know, for the labs, you know, it's really about awarding participation. Really, you know, it's nothing tricky. All right, let's now do a very quick recap about the deadlock freedom lecture, well, last Thursday's lecture. I'll just tell you guys what you should really review when you watch that lecture recording. So from that lecture there, we basically talk about adding 1 and 2. So if you recall what we said last Tuesday about that workflow, whenever you find any unprovable sequence, you got to think about going back to your model and fix it, and then try to regenerate all the proof sequence, and then try to reprove them. Okay. So this exercise here, we decided that we're going to add this and this 2 guards to MLL and MLN, these 2 events. So that's what we decided to do. And then you will see that after you have added these guards as the extra hypotheses, you will be able to prove everything. Okay? So that means as far as invariant preservation is concerned, our model is good. All right? Okay. And then that lecture over there also covered about initializing the system. Typically, this one is very straightforward. I think initialization, usually just initializing some variable to be 0, empty set, empty relation, it should be quite easy to judge. Think about when you do mathematical induction, usually base cases are really straightforward to really justify. What's really tricky is about inductive cases to prove. Okay? Similar idea. Okay? So please go over about this, and then proof obligation, right? How you can establish, how you can generate proof sequence from there. So I'll leave the details to you. Okay? If you got any question, you can still ask me tomorrow, office hour. And then, okay, so that's about proving the sequence invariant establishment. So up to this point over here from last Thursday, we have shown that our model actually after adding the two guards can maintain the invariance and also can establish the invariance, two things. And then we talk about third component about correctness, which is deadlock freedom, which we're gonna pick up as well today in the beginning. Okay? This page here is very important, just to talk about intuition. Okay? What does it really mean? Let's go from this. Our bridge controller is the so-called reactive system. It should always be reactive to external environments, to the user or to the cars or to the traffic light, right? It should always be working. There should not be a moment where no events is enabled. That's really the critical idea. Okay, so let's just go from scratch very quickly. There's always at least one event that's enabled. If all the events are disabled, that's deadlock. That's not good. Okay? So it's unacceptable to really have deadlock. So now, how do we exactly phrase this condition logically? First of all, overall, when you say the deadlock condition, the condition where the system deadlock versus the condition when we say the system is deadlock free, they are exactly the opposite logically to each other. Right? So let's start with this. What does it really mean when we have deadlock? Easy. You basically say the guard for all the events are simply not the case. So in this case, the ML out guard is simply false, and the ML in guard is also false, and both of them must be false. So no event is enabled at this point. And then we did a little bit of simplification, and then we try to say, when I say not the case, it will deadlock. That means it's deadlock free. Right? So I simply apply the negation to this particular deadlock condition, and then I got this one here. So this one here, what does that mean? That means when I say my system is deadlock free, I got either this ML out guard enabled or ML in guard enabled. I just need one of them to be enabled. In that case, my system will be deadlock free. All right? So what you should really pick up from this page over here would be the condition for us to say deadlock. To say there's a deadlock situation versus when we say the system is deadlock free. You got to be very careful because in the written test or in the exam, when I say you may want to formulate certain condition, you got to pay attention to, am I asking about deadlock condition or deadlock freedom condition? Okay, got to be very careful. It's black or white, right? It's logic. Okay, so you can review this, but we'll pick it up a little bit from here as well today. And then this page over here is just talking about the proof obligation rule about deadlock freedom. It's just about all the guards should be at least one of them is actually true. So that's why we got this junction right here, right? It's just or. Okay. And then this table here is also very important to summarize about what's really needed. Okay, let's go over that quickly. When you say you want to establish the invariance, you only worry about the post-states. So when you review the lecture, you want to review why there is no pre-states for the init events. I kind of put some explanation for that, so you can review it. And also, when we talk about invariant preservation, we are really saying, assuming that the invariant is actually holding in the pre-states, we want to prove that it's still holding in the post-states. So both should be applicable. Now, for deadlock freedom, we don't really talk about post-state. We only talk about can any events be enabled. So before any event is even executed or happening, we want to make sure in the pre-states at least one event is enabled. So the deadlock freedom is only concerned about the pre-states, whether any event is enabled. Right? Just go over this table, just make sure you can understand it. Okay. And then inference rule. So that's the second set. Right? So we got hypothesis, we got false on the left-hand side of the turnstile, in which case it's just like a false implies anything will be just true, like a zero of implication. And also, if you got true on the right-hand side of the turnstile, it's as if you got true on the right-hand side, like a consequent for implication. So that's just true. I'm going to revisit about these two as well. Okay? So for these two rules, it's about EQLR and EQRL. So both of them are possible to be used. So today I'm going to show to you how to contrast the usage of this. I'll show you some application. So for now, I'm just going to assume you already went over about the meaning for these two rules and see how to apply them. But I'm going to show you example, but you're going to see some detail as well by yourself. Okay? And then, so that's really, once we got a proof sequence for delta freedom, we try to prove it. Somehow, we cannot prove it, somehow. So this goal over here about D should be strictly larger than 0 is unprovable. Because the only assumption we have as axiom in the current model is D is a natural number, meaning that D should be larger than or equal to 0. Being larger than or equal to 0 does not imply it's larger than 0. So that's why this particular goal here is unprovable at the moment. All right? So what we should really... Hey guys, hey, please, okay? I can hear that, all right? All right, so let's now go on. Okay, it's unprovable, so we're gonna do something about it, all right? So I would like to pick it up from here and do something here, all right? Let's revisit this first attempt. Let's revisit that. When you go over the proof, of course, at some point we're reaching here, right here, okay? I'll make it here, right here. So here in the assumption part, we say n equals d, right? And then the solution tells you that you should really apply EQLR. And then you simply say every occurrence of n should be replaced by d. That's what we're saying, all right? That's something you can actually follow, the video. But now I'm kind of asking you, you might be wondering as well, why can we not go for EQRL? Right? It's a legitimate, actually, application. You will definitely work mathematically. So that's something I would like to explore a little bit. So that one there is really about we have two possible branches of doing the sequence proof, and we might end up two unprovable sequence, but we're going to decide which one might be more useful for us to revise the model accordingly. So in this course, even though things might work mathematically in both branches, you're going to choose the one that's going to be more useful for your system development. That's something I would like to talk about to begin with. All right? So this is really the question we're asking. So what if EQRL is actually used? Okay, I would like to start with this. All right. So let me just copy that sequence there, and then we'll start from there. Okay. So let's say I'm just copying exactly this. Okay, just right here. Okay, I'll start from there. So I would say n equals d. Turnstile n less than d, or n larger than 0. Okay, let me start with that. Okay, that's the sequence I would like to prove. Okay, starting from exactly here. So now, rather than using EQLR, what if you somehow happen to choose to use EQRL? What's going to happen? Okay, let's do that exercise together. Okay, so what I would do is I'm going to do EQRL. EQRL. Let's now review about what this rule is supposed to do, right? Because RLLR might sound a little bit confusing, so let's be very clear, because you might have to do something like this in the test or in the exam. So this one here, let's now review ourselves, right? That one simply means you're going to replace every occurrence of the right-hand side by the left-hand side. Okay, first of all, let me write it down. You're going to replace in the goal, which is right here. I'm going to replace in there. In the goal, every free occurrence. Free occurrence in the sense that the variable name may not be like a dummy variable in the quantifier, right? That's something we kind of learned from the previous math course. When you say a variable is not free, that means somehow bound by certain quantifier, right? Just an aside. Okay? So every free occurrence of the right-hand side by the left-hand side, right? Right-hand side by left-hand side. Let's now do the substitution, right? If you look at that, the right-hand side is D, right here. The left-hand side is N. Okay, let's be clear. Okay, so now what I will do is I'm going to replace every occurrence of D by N. So this means this one here should be replaced by N. Right? That's what I should do. All right, let's do it. After this, I should really get this. I should still keep this equality here. And then I say, so I already did a replacement. So D should be replaced by N. N less than N or N larger than 0. Again, I have replaced the D here by the N. That means I got N here, right? Just make sure you actually did the right order. Okay. When I get to this, I can now try to do a little bit of arithmetic, or I can do monotonicity. Doesn't matter the order. Let me do monotonicity. This equality here has already served its purpose for replacement, so I can get rid of it. I can drop it. Okay. So what I will do is I'm going to drop it. That one is going to give me a smaller sequence right here. That one there is going to be no assumption, N less than N or N larger than 0. All right? Up to this point, I have no inference rule I can use, but you have a safety net you can always fall into. You can use the arithmetic rule if you want to justify. For example, I can say right here, N less than N, obviously false. That one I can take, right? Any number that less than itself should be false. And also false or something should be to something itself, right? So here I can say arithmetic. And here I can simply just put some explanation. I would say N less than N should be equivalent to false. And also false or anything is equivalent to just something itself. Identity for the disjunction. Of course, you can replace the underscore by another predicate name. That's okay. Right? So after this, what we get is we only have to prove something like this. Turnstile, N larger than 0. All right? So don't lose the big picture. What I have shown to you is when we get to this point, let's say you're now in the test. Let's say I want you to prove the deadlock freedom. And somehow by using EQLR or EQRL, you will end up in two different sequences. Either you're going to have D larger than 0 or N larger than 0. Only these two. But they're both unprovable. All right? Both. So you can see right here, this D larger than 0 is unprovable. This one here, unprovable. And also this one here, also unprovable. Right? Now here's a question. Well, mathematically, we're okay with both. Both branches are valid. You just reach some bottleneck. You just cannot really discharge it. Now the question is, which one should we use as a feedback to go back to our model and fix it? That's really the question. Right? So now it's really up to our interpretation. All right? So should we go for D larger than 0 as an extra hypothesis for our model right here? Or should we go for N larger than 0 as the extra hypothesis as our model? Just before I take a Diago's answer, let me help you guys a little bit. Go back to the basics. You have no clue. D here is like a constant. That one is more about what's the maximum number of cars we can have in a compound, right? N here is like a variable. It's about how many cars do we allow ever. How many cars will actually be in a compound, right? This one is keep changing, and this one here should be fixed like a cap. So now we are wondering, should we add this as a hypothesis back to the model, or should we add this as a hypothesis back to the model? Okay, Diago, what did you want to say?
Yeah, we should take D larger than 0 because that's our constant for the maximum number of cars that is are allowed on the island. And it makes more sense to do that rather than to have, as you just said, a variable because it will be okay if no cards are in the end. Basically.
Ah, okay. So you're basically saying, okay, in some way, rather than justifying why we should really choose d larger than 0, why don't we try to justify why we shouldn't choose n larger than 0? Again, why shouldn't we choose it?
Well, it's a valid case or a valid scenario in our problem that there are no cards in the end. That could be, for example, the initial state.
Yeah, it could be initial state. Let's say we start with an empty island or empty island, empty bridge. Well, maybe it's already overnight. No cards are actually in the island or in the bridge, right? So n equal to 0 should be allowed, right? So let me write it down and then I'll recap. So this is more about like learning about how to use mathematics to help your system development. It's not just about math itself anymore. We're going above it, okay? So let's now talk about this one here. So I'm just going to circle this right here and say this is inappropriate to be a hypothesis to be added back. Okay, so this one here may not be a realistic hypothesis to add back to the model because the island bridge, right? Because the island bridge compound may not have any car. For example, when your system is first used, maybe no car has been entering just yet. Well, maybe this like a no car can stay overnight policy, in which case there's no car as well, right? So we know that this one here, even though mathematically valid, but we shouldn't really choose it to improve our system. So that's why we should really try to interpret d larger than 0 instead. Okay, let me recap what we have said so far. What we are saying is, whenever you're trying to discharge some proof obligation as a sequence, you might actually sometimes have some alternative branches that you can choose. You can either use this particular rule number 1 or rule number 2. You might all end up having unprovable sequence. In that way, you have to judge which one might be like a useful assumption to go back and fix your model accordingly, right? Certain assumptions are simply not realistic. Once you add it, it's just not going to be a feasible model, all right? All right, so we don't choose this one, all right? But another lesson we can see is more like a recap about how to distinguish between EQLR versus RL, right? Just be careful, all right? You know, for example, let's say in the test, I'll just give you some abstract idea. If I simply give you, for example, 2 sequence over here, I put in the middle, should we go for EQLRL or EQLR to justify it? In that case, you have to watch out for how the variable has been replaced and work out exactly where is the left and where is the right. All right? So that's something you can also think about when you do the exercise. Let's now move on to interpreting d larger than 0, which is unprovable. Right? And you can definitely see the detailed justification on the slide. I'll just try to go more intuitively together with you. Okay, right here. Okay. So we know that d larger than 0 is something we cannot really prove just yet, but let's interpret that, okay? So we cannot prove it by the current model, and this is our current model. The only thing we know about d is it's a natural number. That's the only thing we know about it. And we know that d is a natural number means d is larger than or equal to 0. That's all we know. And then, first of all, we know that we are not able to prove d larger than 0. Not being able to prove d larger than 0. We are not able to prove it. All right? What does that mean? That means the model itself may have some case where it is going to violate it. That's why you cannot prove it. Okay? Logically speaking. This might be the most critical step to actually get through. Okay? That means the current model that we have may violate it in certain scenario. Okay, let's talk about what does it really mean when we violate this particular sequence that we want to prove. Violated simply means the negation of it is true, right? That means not the case d larger than 0 is actually true in some scenario. Okay? And then let's now simplify that. Not the case, d larger than 0, let's get equation number 1. d less than or equal to 0. So we are saying that it is possible for our current model to have a case where d is less than or equal to 0. And that one actually disallows us to prove this one here. All right? And let's now try to get one more information. We got 1 here, and then this is also something we know, right? The axiom, okay? So we can also put it down as well. So think about this is number 2, okay? I put number 2 here, d larger than or equal to 0. Okay, so let me give some annotation. This is about the condition that's going to violating the goal. And remember, this is the goal that we wanted to prove for deadlock freedom. Okay, and d larger than or equal to 0 is actually a typing constraint for d. If you combine 1 and 2, d equal to 0. So that's exactly the value we're going to look into. All right. So that one there tells us we have a value here, d equals 0. What is so special about d equal to 0? Imagine with the current model, and then I have one instantiation for the model, like a valuation, like a state space, right? If d is exactly equal to 0, what does that mean? The maximum number of cars I'll ever allow is 0. No car should be there, right? Let's take a look, all right? Let's now write it down, all right? So taking this, and let's now try to write it out, okay? I'll put it here. Say d equals 0. And then we know that after initialization, n is exactly equal to 0, no cars, right? So now, there are only 2 events, either ML out or ML in. Which one can happen? One event can only happen if its guard is enabled. Is this guard enabled or is this guard enabled? Right? Let me put it down, okay, to help you. Okay? So now you want to think about the guard. So the guard for ML out. Also the guard for ML in. Right? Let's write it down. ML out n less than d. N less than d. And ML in n larger than 0. That one there. N larger than 0. And we know that d is 0 and n is equal to 0. Right? So now replace n by 0, d by 0, n by 0. 0 less than 0, false. 0 larger than 0, also false. Remember, we actually got a deadlock freedom condition, right? We should put an or between the guards. So now, we're simply going to have 0 less than 0 or 0 larger than 0. Both of them will just evaluate to false. So this would mean the system will deadlock right away. Right after initialization when d is equal to 0. It's the conclusion we can make when we analyze it. Okay, what we have done was we came from this particular unprovable sequence, d larger than 0. We try to interpret that. And then we had a conclusion that when d is equal to 0, after initialization, the system deadlocked right away. So that's not acceptable because for the reactive system like bridge controller, we should never deadlock. So this is something we may actually want to add as an extra hypothesis because we know that's important. If you simply allow the possibility where d is equal to 0, it's going to deadlock right away. All right? So the conclusion is we should really add. So from here, we know that the fix will be we want to add an extra axiom d larger than 0. Okay? That's what you will see on the slides. Okay? That's what we want to do. So once you add this extra axiom, because one of the antecedents for the proof obligation rule for deadlock freedom, we include the axiom. So we got add one more. Okay? Question about this? Okay, I hope that's clear. Let's now go over a little bit. Let's see where we are in the slides, right? So first attempt, we got d larger than 0. So slide number 40 is all about what I just discussed, right? So you deadlock immediately. Okay, so take a look. It's exactly the same flow. Okay. And then how do we fix it? So we are just going to add a new axiom, d larger than 0. All right, that's what we're going to do. So adding this axiom here is much more sensible and also feasible than adding n larger than 0 as an invariance. Right? You shouldn't really restrict the card that may be 0. Right? And this is saying we used to have requirement number 2 just about the number being limited, but now we say it should be positive as well, not just limited. It cannot be arbitrary. All right? So now is it provable? Yeah, Diego.
Wouldn't it be more efficient to modify the definition of D to belong to the positive natural numbers rather than having
Yeah, that would be another possibility. Yeah, I agree with you. So what Diego was suggesting was, it's definitely one possible fix. Okay, I'll put it down. So you got two choices. Either you can say axiom 0, 2, and then d larger than 0. You got two separate axioms together. So this one here just showing that this one here specifically is really to prevent deadlock freedom. Right? On the other hand, you can simply, let's say, get rid of this. Say d is a member of natural number 1. That's also fine. But let's go with maybe like an extra axiom, right? Okay. Both are good. Okay. Logically. All right, so what we'll do now is we're not going to see the second attempt. Okay, I'm going to show you guys just conceptually what's going to happen. Oh, sorry. Let me go back here. All right, right here. So this is the first attempt that we failed before because we got d larger than 0, actually unprovable. Now that we added one extra axiom. Okay, I'll put it here. So we basically got one extra axiom right here. So we got axiom 0, 2, d larger than 0. Okay, so this one here corresponds to basically this d larger than 0 that we want. Okay, right here. And let's see what the consequence is going to be when we regenerate the proof obligation. Okay? Basically, everything will be the same, except we have one more hypothesis to assume. Okay? So let's put it down. You can think about in the beginning, since this used to be axiom 0, 1. All right? So we got also another one, n larger than 0. And this one here, you can make a comment to say is actually that's actually axiom 0, 2. All right. So we are propagating this extra hypothesis all the way through. Let's see what's going to happen. Okay. So that means over here we can also add it d larger than 0, and we make sure we don't drop it in monotonicity. So d larger than 0 will still be there, and then for this part here, we can still keep it, but for this branch, we don't really need it, so we can just drop it, monotonicity. Okay, I'll leave that to you. Okay, so I can simply say d larger than 0 here. And then this one here, d larger than 0 over here. And then make sure you don't drop it, still here. And now you got this. Right? It's propagated all the way to the unprovable sequence that we had earlier. So now is this provable? Ethan? Oh, yeah, I agree. Thank you so much. I agree, yeah. I really meant to write the other way. Yeah, thank you. There we go. Thank you. Yeah. All right, so this one here apparently is provable, right? So this one here is going to be provable by the hypothesis rule. That's something you can also review from last Thursday. All right. So now Della-Freedom will be justified after we have added this extra hypothesis by fixing the model. Okay. And then I would also suggest you guys can try this particular exercise here. I'll leave the page clean. So this is the ultimate Della-Freedom proof obligation. It's a sequence. You know, this is added, right? It's a hypothesis. Maybe you want to take this one here. Maybe just to begin with, you can put, these are all the relevant inference rule you would need to prove it. Why don't you start with this one on a piece of paper and then try it? Okay, maybe after class, maybe not today. Okay, so give it a try. I think it's going to help. Maybe for the written test for sure, but also exam for sure. Exam. Okay, give it a try. Okay, I'll leave it clean. Let's now make a quick conclusion about our initial model, and then we'll take a short break. We'll take a little bit earlier, and then after the break, I'd like to go on to the first refinements. Okay, and we're going to dive into more interesting stuff when we get to the refinement. So this is the actual final version for our initial model. Let's now recap what's going on here. Okay, so to start with, let's see right here. This part over here, constant and axiom. So these contributes to the static part for our system. Static part. And specifically, the axiom right here that we added is really for the purpose of Della-Freedom. Okay, so that was one of the fixes. So that was the fix for proving Della-Freedom. Okay, just remind ourselves. And then the rest will be the dynamic part. Variable, invariance, and also the events, right? Let's also take a look at them, just to remind ourselves over here. So that will be the dynamic part. So that one there is the dynamic part right here. And these two guards used to be guardless, right? Used to be just true. But we found that having no guards for these two events are going to let us fail to prove about invariant preservation. That's why we had to strengthen. We had to add a guard. I'll talk about strengthen and weaken either today or Thursday. Not just yet. Okay. Okay, right, these two. So these two extra guards were added for invariant preservation. Added for invariant preservation. So when you later on, when you review about up to here, for sure, you want to just remind yourself, all we are doing here is we started with something simple. And then we try to show that the model is correct with respect to three criteria. Invariant establishment, invariant preservation, and Della-Freedom. That's all we have been doing in the past number of lectures. Any question about initial model M0? Okay? Okay, so why don't we take a little bit earlier break today, slightly earlier, and then we'll take attendance, and after that we'll do model 1, first refinement. All right, so we're now completely done with the initial model. So it's time to introduce about the first refinements, okay? So second attempt, you guys can do the exercise yourself. I'm also gonna make a PDF version as well on the lecture side, so you can definitely take a look at that as proof as well. Print it out, whatever you like. Okay, I'll make it available before Thursday's class. You can also take a look for studying later. All right? Oh, by the way, guys, so there might be different ways to really discharge this particular sequence. If you do find another way that you want to be double checked by me, feel free to drop by. I'll be happy to learn about it. Maybe I can even create another version for you or fellow student to benefit, right? So feel free. This may not be the only way to prove things, may not be. If you find another way, I'll be happy to know. Okay. Of course, in your exam, if we do want you to prove certain sequence, let's say if I start with this, for example, right? If I start with this particular sequence as a question, I say prove or disprove it, right? When you prove it, you don't really have to worry about following exactly how we did it in the class, as long as you can only apply the inference rule that we talk about, or the ARI, arithmetic, and then prove it, that'll be acceptable. So TA or myself is gonna judge the validity of your answer. Okay. All right, so that's about second attempt, and then we do the summary right before the break. So we say that it's provably correct because we actually prove the proof obligation, right? So that's important to really notice that term, provably correct. Okay, let's now talk about refinement, right? Part of the course title, for this course, part of the title is refinement. Let's see what refinement really is. So somehow we said there's something called correct by construction. We started with the initial model being very, very abstract and simple. And we're going to gradually add in more details into the model. So now for the first refinement, we're going to add some detail to our initial model. Initial model only got some variable called n, but we're going to make it a little bit more concrete. Okay, let's see. Let me go over just some bullet points, and then I'll switch to iPad to visualize what's happening here. So what we're going to have a little bit more concrete perception about a bridge controller. Back in M0, we said that we stay on very, very high in the sky. We cannot really distinguish between the bridge and the island. It's more like a compound. Let's say now we move a little bit closer to the ground. So now we want to see a little bit more closely about this bridge controller infrastructure. So now we're going to make a distinction between the island and also the bridge. That's what we're going to do. All right. So now we're going to split the island bridge compound into two parts. Bridge and island, of course, right? So that's basically what we're going to do. Okay, that's all I need to show. Let's now take a look at the picture. Okay, I want to put it side by side and show you the correspondence. Let's start with this. That's something we have been talking about for a few weeks already, right? So that one there, we got island and bridge compound. No distinction between the two. And we only got two events, ML out and also ML in. All right, now, for the coming few weeks, well, maybe 2 weeks only. We don't have that many weeks left for the course, only 2 weeks. We're going to talk about this particular abstraction. So here we actually got island and we got a one-way bridge. These two are considered different components in the system. We're going to worry about them, okay? And then we're going to see exactly what kind of variables we should really include to somehow measure about the correctness of the system, okay? That's kind of the two pictures we want to put side by side. So we say that this is the initial most abstract model with no distinction between the island and the bridge. And now we are introducing something that's slightly more concrete by splitting the island and the bridge into two components. So let's annotate a little bit just to see what's going on. So let's see here. Let me start with the events. We only got two events before. ML out and ML in right here. Okay, so let me highlight them as well. We got ML out here, and also we got ML in. These two events. We call these now the abstract events because now we have two models in the context. We say that this is the abstract model. This is the concrete model. Abstract and concrete. Okay, concrete in the sense that more details. So here we call these two the abstract events. Okay? And then, on the other hand, we say that these two are the concrete version of the events, ML out and ML in. They're basically the same events, but now we're making them more concrete. Okay? So I'm still going to put a green here, ML out and ML in. Right? So these two are now the concrete version of the events. Concrete version. Okay? And since now we actually have to distinguish between the island and the bridge. So now we want to somehow distinguish between when a car goes from the mainland to the bridge versus from the bridge to the island. So now we get to distinguish between these two. So that's why we got separate events. Before, we only say from mainland to the compound, from the compound to the mainland. That's from before. But now we're going to make it more sophisticated. It's going to be 4 events, from the mainland to the bridge, right here. And from the bridge to the island. And then from the island back to the bridge, and then from the bridge back to the mainland. Right? These are the 4 events. That's kind of the sequence you can expect for any car. All right? So let's now also put this. IL in and IL out. Okay, just to remind you, whenever I say ML and IL, so ML means mainland, IL means island. Okay, just a convention for naming. So here for IL and IL out, they don't really exist in the M0. They're like a new events. So these are called the new events. So in some way, you can think about the ML, MLN. They are called old events. And old events. So for the old event, you just got a version about being abstract or concrete. Well, let's make a table. It might sound a bit confusing already. Okay, let's now make a table. Okay, let me put it here. Oh, you know what? Let me just do that on a separate page. That would be better. First of all, let's now talk about a table here. There are two dimensions. Either you can say the events are either old or new. Old or new. Or you can say it's either abstract or concrete. Abstract or concrete. Okay? In our cases, in our particular case, old here is really about, we're talking about whatever that exists in the abstract model, which is M0. And also abstract means that exists, like a version that's in M0. Okay? So think about in this way. Old or new is more about existence of the events. It's already declared in that particular model. And abstract versus concrete is more about the version that we have. Okay? Two dimensions to describe. Okay? And for the concrete, it's really about here, concrete is really about M1. And the new here is about M1. Okay? Okay, let's see what we have in this table here. Later on, we're going to introduce another refinements later. So it can be M2. So we could do similar table. We'll do that later. Okay. So now for here, that's something we have been studying. Okay? So that's one here will be ML out, ML in. ML out, ML in. So these are the two events that we have been studying right here in the summary. All right? And then, what about here? We're still talking about ML out, ML in. But somehow, you think about in Java term, not very good analogy, but it's more like an overridden version or redefined version in a subclass. A little bit like that analogy. Okay? So these two are I'll put a different color just to show you that even though we are referring to the same events, but they're different version. Okay? So they are more like ML out, ML in as well. ML out, also ML in. Okay? So we're talking about the same two events, just the abstract version in M0 versus the concrete version in M1. All right? What about the new here? Okay, new, simple. New is something that doesn't exist in M0. So this one here does not apply. Okay? We can ignore this one here. Not applicable. And new is simply referred to any events we add in addition in the M1. So that one is going to be IL out, IL in. IL in, also IL out. So these are the events that only exist in the new model. So these are the events only existing in the refinements. Simply because we have now split between island and the bridge. Okay? Let me add another diagram here just to show you the trend of the refinements. And then we'll go back to the diagram. Okay? Okay, let's now try to look at that from a slightly different angle. Okay? So we started with M0. All right? And then we say that one there is refined right now by M1. Okay? You can think about the arrow here simply means refined by. Again, not a very good analogy. You can think about M1 extends M0 in Java term in some way. Okay? And then, so here we say that when you compare these two models, M0 versus M1, you say that M0 is the more abstract one. M1 is the more concrete. Okay? And of course, in this case, we actually got the two events. So here we got ML out. Also, we got ML in. And here we got a concrete version for the two events. So here we got ML out as well. And also we got ML in. Of course, we also got new events. Also IL in. Also IL out. New events. Right? Now let me add one more. Okay? We're going to see another refinement later after refinement number 1. So it's going to look like this. It's like another layer right here. And that one is going to be called M2. Okay? Refinement number 2, basically. So you can think about this one here is also M1 is refined by M2. Refined by M2. Okay, let's not worry about exactly what events we're going to put there. We can worry about that later. But also, when we compare these two models right here, so when you compare M1 and also M2, when you compare these two, it's also relative. You will say that M1 is the more abstract one, and M2 is the more concrete one. So abstract and concrete, they are not really absolute. They are more like a relative concept. Okay? So this one is the abstract one. And this is the concrete one. So you can see the same model here may be considered as concrete or considered as abstract, depending on what's the other one you're talking about. Right? For M1, if you're talking about comparing with M0, then it is a more concrete one. If you're comparing M1 against M2, then that's the more abstract one, depending on where you are. Right? So that's basically the roadmap of the rest of the semester. We're going to see M1 and M2 to learn about the, more concepts. Okay? Let's now go back to the abstraction diagram. Okay? Let's now see a little bit more. What we're going to see is here, what we had before, we have a single variable, n. Right? That's a single variable. Okay? N here. Okay? You know what? Let me just let it stand out. N here. All right? And another way, I want to do a little bit more layer right here. Think about the compound of island and the breach right here. Right here. Right? The green one is including the island and also the breach. This is the abstraction for M0. So this is really the abstraction for M0. And now for M1, we're trying to split them into two parts. We're basically splitting that into the island and also the breach. These two. And then we're going to have different variables. We used to have just the n, the green one. We used to have just n to really talk about how many cars are in this particular compound. But now since we split them into two parts in the M1, so now we're going to have 3 different variables. I'll mention them first of all, and then we'll see more. Okay. So we're going to say there will be a variable called a here. Okay, let me just double check. I don't want to give you any wrong information at this point. Okay, good. We got a here, we got b here, and also we got c here. Okay. In M0, we only talk about n. Simple. But now in M1, we have added some concreteness to the model. We're saying that how many cars are really going this way? Call it A. How many cars are in the island? Call it B. How many cars are moving from island back to the mainland? Call it C. We got 3 measures over here in M1. So we have to somehow see how these two models are going to play out together. Okay. So let me just say a little bit more. So when you go from n0 to n1, right? Basically, you have added some concreteness. Added some concreteness. I.e., you have some one-way bridge. We're going to see exactly how to specify the one-way bridge. We got A, B, and C. So these are the three variables we're going to consider in a concrete world. All right. And for this first refinement, we're going to address about these two requirements, requirement 1 and 3. We're going to talk about this a bridge. Okay, let me just say this. So there is a bridge, and also the bridge is actually one way. So these are the added concreteness for M1. Okay, we're going to see exactly how to express them mathematically. So there's a very important sentence there on the slides. I'll show that to you very quickly. So that's something we just spoke about, right? So now this last sentence here. So now once we have declared all the necessary variables, we call the concrete variables in M1. We are then obliged to really prove the added concreteness is still consistent with the initial model. So that's about refinement proof. That's something we'll do in a couple of lectures coming. Okay. The last bullet point is really important. That's exactly what we're going to talk about in this not just in this class, but also Thursday and also onwards. Any questions about this diagram here? Okay. Chris, yeah.
So you say that the bridge is, to understanding, is that a bridge one-way street or two-way street?
The bridge is one way only. Oh, one way in the sense, in the following sense. You might, okay, I see what you mean. One way in the following sense. When there's a car going this way, oh, sorry. When the car is really going this way, there should be no car going this way. There should be no clash. When I say one way, either from mainland to island, or could be from island to mainland, but not at the same time.
So if A is a number larger than 0, then C should be 0.
Something like that.
Okay.
Something like that. Well, that's what something we'll have to encode. It's more like an invariance we got to do, right? So intuitively, we know the safety property is either we go from mainland to island, or we go from island to mainland, but not at the same time. Okay, that's something we have to actually do. Okay. 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 So let's now move on to the next part. We've got about maybe 15 minutes or so. So let's now see how much we can do. Okay. Okay. Let's now go over. Okay. Let's now talk about the actual variables and also some invariants. That'll be interesting to go over. Okay. Okay, let me just go. Let me focus on this directly. Okay, and then we'll do the events design next time. Okay. So the dynamic part for the model is going to be A, B, and C. So let's now annotate it. We got A here, we got B here, and also we got C here. Okay, so let's say A here. A here is the number of cars from mainland to island. They're on the bridge. Symmetrically, we also got another variable here, C. That's about the number of cars from island to the mainland. Oh, by the way, of course, the mainland is right here, right? Right here, okay? What about B here? B here is about the number of cars that's already off the bridge. They're just in the island. So the number of cars in the island, island. Okay. What we want to do now is let's go over quickly the decoration. So we have the static part is really the same as before. We still got a D here. It's more like an inherited from M0. Okay. So we got the maximum number of cars, and also the natural number, and also D larger than 0, right? That's something we fixed already, so we are using it, right? So we got A, B, and C. So these three are the very straightforward typing invariants. Specifying just a type. typing constraint. All right. Let's now try to work out these two. But that should be very straightforward. Okay. So we need two invariant here, but they are of different nature. Okay. Let's start with this. Since we now have put it in this way. Okay. Let me just try to draw that picture again. If you only consider M0 right here, it's going to be non-distinguishable between the island and the bridge. In that way, we only got N. Oh, sorry. And that is from M0. But now in M1, we got A, we got B, and we got C. Right? So now, invariant number 4 has a very special name. It's called a linking invariance. Linking invariant is saying whenever we got two models existing at the same time, they're somehow related to each other. One is more abstract, the other one is like a refinement and more concrete. How do we draw a connection formally between all the variables? That's what we're going to do. All right? So invariant number 4 is what we call a linking invariance. They got different names in the literature. Either you can say it's a linking invariance, we can say it's a gluing invariant. It's trying to glue the M0 and 1. Gluing invariance. Any suggestion? How do we draw between the connection between N, A, B, and C? Well, that one should be rather straightforward, right? I'll take you first. Yeah, go ahead.
A plus B plus C equals N.
Yeah, exactly, right? Yeah, great, that's obvious, right? But it's very important to see that visually and that we can work out logically, right? Exactly, thank you. So this one here is exactly that. That one there is going to be N equals A plus B plus C. So this part here comes from M1. And this part here comes from M0. Okay, that's good. That's invariant number 4. Invariant number 5, which your fellow students somehow thought ahead already, right? That one is what we call a safety property, which is important, okay? If you're dealing with safety critical or mission critical system, there will be some properties you want the system to maintain its integrity, so it's very important. So safety invariance. So safety invariance saying bridge is one way, meaning that there should be, well, how about this, put it this way. There should not be a scenario where we got some cars going this way and some cars going this way and we get a clash. There shouldn't be. Any suggestion? Of course, we gotta allow traffic both ways. It's either be this way or this way, but not both at the same time. Any suggestion about what we should put for invariant 5? Think about this way. If you only got the variable N back in M0, there's no way for you to specify this safety constraint because there's no distinction between the bridge and the island. But now, in M1, we do have all those variables that's necessary for us to express this safety constraint. Anyone else would like to try? It's okay to be wrong. Ivan, go ahead.
Maybe wrong. I'm thinking of like A greater than 0 and C equal to 0 or A equal to 0 and C.
I see what you mean. So invariant number 5, okay, let me put a star here. I believe what you're trying to say here is A greater than 0 and C equals 0, or C greater than 0 and A equals 0. Yeah, you're thinking that, right? Okay. It turns out it can be simpler. Okay. It can be. A plus C equals A?
Or A plus C equals C.
Oh, interesting. Interesting. Okay. There's another alternative version. I'll put it here. That one actually sounds also very interesting. A plus C equals A. Or A plus C equals C. This one actually is kind of equivalent to what we're going to have, all right? So what your fellow student is saying is either A plus C is actually going to be all the cars really just going this way, or it could be all the cars is really going this way, like here. But why don't we simplify that, right? If we simplify that, what does that mean? Yeah, because you can cancel this out, right? Well, you know, it's good. C equals 0. And also, this part here will be cancel this out, A equals 0. That's exactly the ultimate answer. You just got to simplify that. But conceptually, you're right. So I think that even you're also quite right. I think that this one here just can be simplified further. Yeah, good. All right. So what we're going to have is the ultimate version. So it's going to be A equals 0 or C equals 0. This is saying either there's no car coming from this side or there's no car coming from that side. So we are safely guaranteed there's not going to be a clash. Okay? All right, question.
Can't you just say A does not equal C?
Huh?
Can't you just say that A does not equal C?
Oh, sure. If you say A is not equal to C, right? Good question. Let's try. Question here. I like that. I like that. B. You say A is not equal to C. Okay? Of course, if I somehow say that's right, or I can say that's wrong, right? If that's wrong, I got to give you some witness to show that it's a violation, right? Okay? I'll just say that right away. You just think they're not equal to each other. What about A is equal to 3? C is equal to 2. So what does that mean? You got 1, 2, 3 cars going this way. You got 1, 2 cars going this way. You got a very severe clash, right? It's not going to work. Because when you say A is not equal to C, it has nothing to do with whether either one of them should be 0. Because for that to be safe, you've got to make sure one way has no flow. So you have no risk of clashing the cars. Okay? Yeah, go.
Could you also say that A times C equals 0?
That one actually from last year, somebody mentioned as well. Very good. I also like it. Okay? You guys are very creative. That's nice. By the way, this is something I heard the first time after teaching this a few times. That's good. Okay. So what Diego said was another version. Okay, I'll put it down as well. This one is also worth discussing. It's actually on my notes. I just forgot to mention. What about when you say A times C equals 0? Mathematically, I absolutely agree with you. Because in order for these two values, multiplication to be product to be 0, one of them must be 0. There's a drawback. Mathematically, yes, that's kind of equivalent. But the problem is, when you actually want to use this as a hypothesis, it will be more difficult for you to actually prove the goal. So that may not be, it's more like a practical concern. Mathematically, yes, but to really help us prove some goal or sequence, this may not be the best candidates. Okay? Okay. So this one here is valid, but hard to use as hypothesis. All right, like that.
Also mean for rodent, like will rodent also have issues?
I think a rodent, they might have certain like axiom behind the scene about multiplication or maybe some arithmetic. That one I'm not exactly sure. It depends on the heuristics of the prover. Yeah. But on the paper, maybe you can just maybe add some lemmas yourself, and then use it, right? All right. Question.
I was confused. If the bridge is empty, then how can we distinguish there is no vehicles? Like, which direction it is?
That's okay. In this way, since we want things to be safe, what's the safest bridge when there's no car? What's the safest bridge controller when there's no car? Right? So we're kind of talking about separation of concern. Invariant 1.5 is only about there's no crash. We just got to make sure the flow either way is actually empty. Whether or not it's really about the whole thing being empty, that's okay. It's one possibility, but it's okay. It's still safe. May not be very useful, but it's still safe. Yeah. All right, good. So guys, I would suggest we end a little bit earlier today, if you don't mind, okay? Because I think the next part there is going to be a little bit tricky. We got to work out exactly how to define the guards for ML out and ML in. All right? So let's now continue from Thursday, but make sure you catch up with the lecture for Daylight Freedom. Okay, I'll see you on Thursday.